Good morning, students. Here the module 3 is covalent bond. The valence bond theory is available to watch in the earlier video. You can hear the molecular orbital theory in this session. Now, I wish to provide a thorough description of molecular orbital theory. The instructor of this video is Mrs. P. Arunajyoti, Assistant Professor in Chemistry, St. Joseph's College for Women. By the end of this chapter, student has able to outline the basic quantum mechanical approach to deriving molecular orbitals from atomic orbitals, describe the traits of bonding and anti-bonding molecular orbitals, calculated the bond orders based on its molecular electronic configurations, write the molecular electronic configurations for both the homonuclear diatomic molecules as well as heteronuclear diatomic molecules. The contents of the molecular orbital theory are introduction of molecular orbital theory, postulates of molecular orbital theory, LCAO method, characteristics of bonding and anti-bonding molecular orbitals, construction of molecular orbital energy diagrams, MOED of homonuclear and heteronuclear diatomic molecules, and the last one is hydrogen bond. Molecular orbital theory. Why would we study molecular orbital theory? What is a molecular orbital theory? It is the application of quantum mechanics to the description of the electronic structure of a molecule is known as molecular orbital theory. It is often known as MOT. It is developed at the beginning of the 20th century by F. Hund and R. S. Mulliken in 1932. It is one of the most productive models of the chemical bonding. What is the purpose of introduction of molecular orbital theory? The purpose of introduction of molecular orbital theory is to overcome the defects, whatever the defects arising from the valence bond theory. As we all know that the valence bond theory fails to explain about molecular orbitals, isn't it? It does not explain the stability of the molecule. It is unable to explain the paramagnetic and diamagnetic effects of the different molecules. All these limitations arising from the valence bond theory was cleared by molecular orbital theory. Molecular orbital theory in general involves a lot of complicated mathematics. However, the fundamental ideas behind the theory are very easy to understand. It involves sophisticated hybridization models. Since the phenomenon occurs in a three-dimensional region of a space, it is symmetrical about the imaginary line that connects the centers of the two nuclei. We know that molecular orbital theory treats a molecule's electrons as moving under the influence of its atomic nuclei rather than assigning them to specific chemical bonds between atoms. According to quantum mechanics, electrons are described as molecular orbitals, which encircle two or more atoms in a molecule and have valence electrons separating the atoms for the spatial and energy characteristics. This study of chemical bonding was transformed by molecular orbital theory, which approximated bound electron states as the linear combination of atomic orbitals. Density functional theory or other methods are also used to approximate these values. Let us see the postulates of molecular orbital theory. The first postulate of molecular orbital theory tells us that the atomic orbitals combine together to form a new molecular orbitals. When the two atomic orbitals combine together, loses their identity to form a new molecular orbitals. Let us take an example, that is hydrogen molecule, for understanding the first postulate of molecular orbital theory. Here the hydrogen molecule H2 molecule is the combination of two hydrogen atoms. Each hydrogen atom carrying one electron in its 1s atomic orbitals. When these two 1s atomic orbitals of the two hydrogen atoms combines together to form a new molecular orbitals. Move to the second postulate. The number of molecular orbitals equals to the number of combining atomic orbitals. How many number of atomic orbitals involved in the overlapping must be equals to the number of molecular orbitals. Let us take an example. Suppose if you combine two number of atomic orbitals, the obtaining molecular orbitals are also equals to the 2. Suppose if you take the overlapping between the 6 atomic orbitals, the formation of the molecular orbitals are also 6. Move to the third postulate. The third postulate tells us that atomic orbitals should have a comparable energies. The atomic orbitals of similar energies can actively involving in a overlapping. For example, the two 1s atomic orbitals of the similar energy can actively involving in the overlapping to form a molecular orbitals. When you are taking the two different types of orbitals like 1s atomic orbital and 2s atomic orbital, there is no formation of molecular orbitals due to its much energy gap between the 1s and 2s atomic orbitals. So the atomic orbitals should have, it must possess a comparable energy. Atomic orbitals are monocentric, whereas the molecular orbitals are polycentric. Means the electron of the atomic orbital is influenced by the single nucleus is termed as monocentric, whereas the electrons in the molecules are influenced by the more than one nucleus is termed as polycentric. Coming to the next postulate, the molecular orbitals can be divided into two types. Those are bonding molecular orbitals and anti-bonding molecular orbitals. Always bonding molecular orbitals tend to occupy the lowest energy levels. Means it has a lowest energy than that of the parent orbital. When the bonding molecular orbital energy is low, its stability is more. The sigma and pi orbitals are bonding molecular orbitals. Anti-bonding molecular orbitals tend to occupy at the highest energy levels. Means the energy of the anti-bonding molecular orbitals are greater than that of the parent orbitals. So that when its energy high, its stability becomes less. Sigma star and pi star are anti-bonding molecular orbitals. How do you differentiate bonding and anti-bonding molecular orbitals? You should indicate the anti-bonding with a star symbol. So it is a sigma star and pi star anti-bonding molecular orbitals. Whereas bonding molecular orbitals, there is no star mark on the sigma and pi bonding molecular orbitals. Next postulate is bond order is always directly proportional to the stability of the molecule. When the bond order of any particular molecule is greater, its stability is also increases. When the bond order is decreases, its stability is also decreases. The next postulate is always while filling up of the electrons in molecular orbital energy diagrams, we have to follow the three rules. Those are Aufbau principle, Pauli's exclusion principle, and the last one is Hund's rule. According to the Hofbauer principle states that always we have to fill the electrons according to their energy states. What is Pauli's exclusion principle? It states that no two electrons in an atom can have the same set of four quantum numbers. Means when the two electrons in the same orbital, the values of principal n, azimuthal L and magnetic M1 quantum numbers are same, but where is the variation occurs? The variation occurs at the last quantum number, that is spin quantum number. Why? Because one electron in upward direction, another electron in a downward direction in an orbital. They are carrying the opposite spins. Okay. So, according to the Pauli's rule, the two electrons carrying the similar azimuthal principal magnetic quantum number, but the spin quantum number is different. The last rule is Hund's rule. Hund's rule states that no pairing of electrons takes place until each orbital belonging to the same shell got one electron each. Means you have to fill up the electrons in the lower orbits first. After filling up of the electrons in the lower orbits, you must go to the next orbit. All these are the rules we have to follow for filling up of electrons in the molecular orbitals. All these are considered as postulates of molecular orbital theory. Next, LCAO method, linear combination of atomic orbitals. Molecular orbitals can generally be expressed through a linear combination of atomic orbitals. These LCAOs are useful in the estimation of the formation of these orbitals in the bonding between the atoms that make up a molecule. The Schrödinger wave equation used to describe the electron behavior for molecular orbitals can be written in a method similar to that for atomic orbitals. It is an approximate method for representing molecular orbitals. It's more of a superimposition method where constructive interference of two atomic wave functions produces a bonding molecular orbitals, and by destructive interference of two atomic wave functions produces a anti-bonding molecular orbitals. Through constructive interference, we can get the bonding molecular orbitals by the addition of the two atomic wave functions of the two atoms. While the through destructive interference, we can obtain the anti-bonding molecular orbitals by the subtraction of the two atomic wave functions of the two atoms. Move to the next slide. Formation of molecular orbitals. There is a possibility of formation of two molecular orbitals. Those are bonding and anti-bonding molecular orbitals. Bonding molecular orbitals can be obtained through constructive interference, whereas anti-bonding molecular orbitals can be obtained through destructive interference. As we all know that, like that of an electron, orbitals also exhibit dual property, that it has wave-like property and particle-like property. When the psi A and psi B representing the amplitudes of the electron waves of the atomic orbitals of the two atoms A and B added together or constructive each other to form bonding molecular orbitals. It can be represented by the equation phi equal to psi A plus psi B. If you observe the second case, here when psi A and psi B indicating the amplitude of the electron wave of the atomic orbitals of the two atoms A and B subtracted each other or destructive each other to form anti-bonding molecular orbitals. It can be represented by the equation phi equal to psi A minus psi B. If you observe the first case, here the two wave functions are come closer to each other. They are added together to form bonding molecular orbitals. But in second case, the two wave functions are far away from each other to form anti-bonding molecular orbitals. This is the way of formation of molecular orbitals. As we all know that there are two types of molecular orbitals, bonding and anti-bonding molecular orbitals. How can we get the bonding molecular orbitals? Bonding molecular orbitals can be obtained by addition of wave functions of waves of two atoms. Means these are formed by additive effect or additive overlapping of the atomic orbitals, so that the amplitude of the new wave is given by the expression that is phi equal to psi a plus psi b. In bonding molecular orbitals, the probability of finding electron in the internuclear region is greater than that of the combining atomic orbitals. Means wherever the electrons present in the bonding molecular orbital resulted by the attraction between the two atoms. As a result of this attraction, bonding molecular orbital has lower energy and it has greater stability. We know that energy is inversely proportional to the stability. When the energy is lower, stability becomes high. When the energy is greater, stability becomes less. Always the bonding molecular orbitals tend to occupy at the lowest position, so it attains greater stability. Look at the pictures. In the first picture, the 1s atomic orbital with a positive sign overlaps with the another 1s atomic orbital with a positive sign to form sigma 1s bonding molecular orbital. Look at the second picture. The negative sign of 2px atomic orbital overlaps or combines with the negative sign of 2px orbital to form a sigma 2px bonding molecular orbital. Here the two orbitals with the same sign combine together to form a bonding molecular orbital. The region at which the electron density is maximum is called overlapped region. In this overlapped region, both signs of the two atomic orbitals must be equal. Look at the third picture. In the third picture, the 2px atomic orbital combines with another 2px orbital. Both the positive signs gets overlapped and both negative signs gets overlapped to form a pi 2px bonding molecular orbital. Here also the same sign overlapping takes place between the two 2px atomic orbitals to form a pi 2px molecular orbital. What is the difference between second picture and third picture? When you keep the two atomic orbitals, those are p atomic orbitals, in a horizontal position, here the overlapping occurs by end to end or axial overlapping takes place to form a sigma bond. While in case of third picture, there is a overlapping takes place between the two atomic orbital by lateral overlapping to form a pi bond formation. If you keep the two atomic orbitals in a horizontal position, we will get the sigma bond formation. While in the case of third picture, the two atomic orbitals means you have to keep the two atomic orbitals in a vertical position, then we will get the pi bond formation. That is the differentiation between the second picture and third picture. So here we can observe the different types of bonding molecular orbitals like sigma, pi, delta. All these are the examples for bonding molecular orbitals. Coming to the anti-bonding molecular orbitals are formed by the subtraction of wave functions of waves of two atoms. Means these are formed by the subtractive effect of the two atomic orbitals. So that what is the amplitude? Amplitude of the new wave is given by expression that is phi equal to psi a minus psi b. The probability of finding of the electron in the internuclear axis or internuclear region decreases due to the repulsive forces operated between the two atoms. As a result of these repulsions, always the anti-bonding molecular orbitals tend to occupy at the highest level or highest energy, shows the least stability. Look at the pictures. If you observe the first picture, the 1s atomic orbital with a positive sign overlaps with another 1s atomic orbital carrying negative sign to form a sigma star 1s molecular anti-bonding molecular orbital. Due to the repulsive forces between these two atoms, they are far away from each other, which results the sigma star 1s anti-bonding molecular orbital. Observe the second picture. Here the negative sign of one of the 2pz orbitals overlaps with the positive sign of the another 2pz or atomic orbital to form a sigma star 2pz anti-bonding molecular orbital. Here these two atomic orbitals are in a horizontal position to make a sigma bond formation. Here also we can observe the overlapping between the two opposite signs of two atomic orbitals. Moving to the next picture, here the 2pz atomic orbital combines with another 2pz atomic orbital to form pi star 2pz bond anti-bonding molecular orbital. Here the two atomic orbitals with different signs are far away from each other, which results the pi star 2pz anti-bonding molecular orbital. We can observe these two p atomic orbitals are in a vertical position, leads to the formation of pi star 2pz bonding anti-bonding molecular orbital. It is the information about the bonding and anti-bonding molecular orbitals. All the images in this video have been taken from Google Chrome. Thank you.